Hi, I'm Rohan Sanapati. This is a project I did exploring one of the most famous patterns in math, the Mandelbrot set. I asked a simple question: what happens if we change one number in its formula? And that led me on a surprising journey through math, simulations, and code. So, what exactly is a fractal? Fractals are patterns that repeat themselves at infinitely many levels. If you zoom in forever, you still see the same shape. You can find them in broccoli, snowflakes, or even lightning bolts. In math, they're created by repeating a rule over and over again, and often they're generated using computer code. Fractals are both beautiful and useful. They appear in animation, architecture, and even biology. The history reveals what we know and what we don't know about the Mandelbrot set. It was first visualized in the 1970s using computers. It has an infinite perimeter and perfect symmetry across the real axis, but some things are still unknown. We don't know its exact area, just an estimate. And even today, it's a simple formula with surprisingly deep mysteries. The Mandelbrot set comes from a very simple formula: f of z equals z squared plus c, where z is a complex number and c is a constant. Start with z equals 0, plug it into the formula, and repeat. If the number stays small, bounded, we keep the point. If it grows too big, it escapes, or diverges. We do this for millions of points and color them based on whether they stayed in or escaped. The result is this incredibly detailed shape that seems to go on forever. Now, my research was about changing the formula slightly. Instead of z squared plus c, I tried z cubed, z fourth, and so on, all the way to z to the power of 1000 plus c. These are known as generalized Mandelbrot sets. To explore them, I used Python and something called the escape time algorithm. It generates a grid of complex numbers, then checks which ones escape and which ones don't. The results were fascinating. Each time I changed the exponent j, the shape changed dramatically. Some had sharp edges, some looked like flowers, and others became perfectly round. After running several simulations for many values of j, I noticed some clear trends. First, the area of the Mandelbrot set increased as j got bigger. I plotted these areas on a graph, representing each point in Cartesian form, j comma area, and found a curve. Second, for really large values of j, the set always stayed inside the unit circle, a circle with radius 1. This was conjecture 2. Third, the escape radius, the value we use to decide whether a point leaves a set, got smaller. Normally it's 2, but my results suggest that 1 might be enough for large enough j. And finally, the area of the set approached pi, the area of a unit circle. I compared my curve to the line y equals pi and saw the two values getting closer and closer. And one visual pattern stood out. When I plotted z to the power of 20 plus c, the shape had 19 petals. This wasn't a coincidence. For every j, the number of petals was j minus 1, and that's when I realized this was linked to something called roots of unity, or special points evenly spaced in a circle. The notion of petals led me to explore symmetry. I noticed these sets had rotational symmetry. You could spin them and they looked the same. They also had reflectional symmetry. You could flip them across certain lines. I didn't stop at observing it visually, however. I mathematically proved it. I did this using two lemmas. 1. Certain reflections preserve the size of a complex number. And 2. Reflecting z to the power of j gives the same result as raising the reflection of z to the power of j. These lemmas led me to rigorously prove symmetry for specific cases: z to the power of 4, 5, and 6 plus c, using advanced algebra and geometry. Besides theoretical problems, fractals have real-world applications today, such as cryptography. Their complex patterns can be used to create more secure encryption systems, which is central to cybersecurity. And as I move forward, I'm hoping to apply my knowledge to practical applications in the field of dynamical systems and contribute to the broader field of computational mathematics. Thank you for listening.